Let's look at circular motion for objects moving in a vertical circle. This would be something like a Ferris wheel. So as this Ferris wheel rotates clockwise, each of the passengers has a tangential velocity. Each particle of this Ferris wheel will have a center-seeking acceleration. A vertical circle could also be an object attached to a string, and that object swings around in a vertical circle. It doesn't even have to make a perfect circle. It could just be an object like a swing, swinging back and forth, and you have a child sitting on the swing, enjoying the motion, swinging back and forth, and a radial distance from some pivot point there. All these cases have something in common, and that is that the object is moving in a circular path, whether or not it's a complete circle or it's just a piece of the circle, like the swing here, where it's just an arc or a piece of the circle. And that is there's an acceleration directed towards the center of the motion for all of them. Similarly, the top of a hill or the bottom of a hill are both cases where an object is moving through an arc. So when a car moves over a hill, or in the dip here, since both the hill and the dip have a radial component, there is also a center-seeking acceleration, center-seeking forces on both of the objects. So let's take a look at the top of the Ferris wheel or the top of a hill. They're very similar situations where the object is moving across the top part of the arc for the Ferris wheel or the top of a hill for the car, and the object is up here at the top, and there is a radius or radial component there to look at for this shape. So there's our object up here. And so if the object is sitting on that surface, so like when you're sitting in a car or when you're sitting in the chair on the Ferris wheel, we would draw a free body diagram of all the forces acting on us. The normal force is up and the weight force is down. The forces are not balanced because I know that there is a tangential velocity of this object, and that tangential velocity on this object that's moving in part of an arc here means that there is a center-seeking acceleration. There is an A sub c is equal to v squared over r. So if there's an acceleration, then that means that the sum of the forces is not balanced, but would be equal to MAC. So let's sum the forces in the vertical direction. Now, there is a center here, and so let's let the center, or towards the center, be the positive direction. So let's let that be our positive direction there. And so that means that the gravitational force is pointing towards the center, and I'm going to let that be positive. And the normal force is pointing away from the center, so it will be negative. So let's sum our forces then. So then our gravitational force is positive minus the normal force, which would be negative, and that would equal m times a sub c. Now, let's look at what each one of these pieces represents. So we have the weight, so that would be m times g, minus the normal force is equal to mv squared over r. So from here, we could determine what is the normal force acting on the car. Now there is, or the object. Now there is an extreme case where the car or the object leaves the circle. So if the car or object leaves the circle, that means that the normal force will be equal to 0 because it's not touching at all. And so then that means that my weight, mg, minus 0 would equal mv squared divided by r. Now let's do a little algebra here. So we'll have mg then is equal to mv squared over r. Now I can divide by mass on both sides. So if I divide by mass on both sides, that will cancel the mass out. And so I will be left with g on the left side and v squared over r. So that means that my velocity would be equal to the square root of r times g. Now this has a special name. It's called the critical speed. If an object moves faster than the critical speed at the top of the hill, it will leave the hill, it will leave the surface. So anytime you are on a roller coaster or any sort of ride where you feel weightless at the top, it means that the object, the car you're riding in, is reaching or at or even greater than the critical speed. Now let's look at the bottom of the hill. So when the object's at the bottom of the hill, it's in this arc. So let's draw a free body diagram of all the forces. We've got the weight force straight down, and then there is a normal force straight up because the surface is pushing up on the object. Now the center is above the object in this case. So let's make above the object the positive direction and below the negative. So when we sum the forces, they equal ma sub c. This is because it's moving in a circle. So then we have the normal force up, the weight force down. That would equal ma sub c. Now, substituting in what I know that f sub g is mg and ac is v squared over r. So then I could use this to determine the normal force or velocity, whatever it is I might be looking for in a problem like this. Now, if we look at a special case, we're like in a loop-de-loop. This is like you're riding in the car and you're going to go upside down and the loop has a radius. There is a case where we're upside down, so draw your little person upside down. And the little person is at the top of the loop. The weight force is straight down towards the center of the earth, like always. But now the seat is pushing on the person, also in the same direction down towards the center of the circle. And the center of the circle is below the person's head, so make that the positive direction. So again, because the object is moving in a circle, there is a unbalanced force because there is a center-seeking acceleration. But in this case, both the normal force and the weight are in the positive direction. So let towards the center be positive. Substituting what I know, force normal plus m times g would be equal to m v squared over r. Now, a special case of this is if we were just to make it through the loop. So you know, if you just make it through the loop, you're swinging something around and it just makes it through. In that case, the normal force is 0. So if we use the equation from above, the normal force plus the weight, mg, is equal to ma, and a is v squared over r. Substituting in for the normal force 0, this could be a tension force too, so equals m v squared over r. Then I can write this as just being the weight, mg, is pointing towards the center, so it is the center-seeking force. So mv squared over r, I can divide by m on both sides. Then I'll have g is equal to v squared over r. But then typically we write that as v is equal to the square root of rg. And this is the same critical speed equation that we derived earlier for when you're on top of the Ferris wheel or over the top of a hill. But in this case, instead of it being the maximum speed to stay on the hill, this is the minimum speed to just make it through the loop and not fall off.